from GEO Protocol from Ukraine. Yes.
Well, thank you guys and girls.
Yeah, a few words about you and about the project, and you go.
So, thank you for coming, and thank you for the attention. I really expect that my talk would be really useful for you guys that are trying to build some kind of Web3 cool stuff. So, let's talk about consistency of the operation itself. And I will try to begin my deck with some little information about why do this whole thing is really valuable for the Web3 and why we should try to make it why we should try to implement this into the Web3 and why we should try to not rely into the solution on a classic web and what treatness they are providing to us today. So let's try to compare current world and that one we all trying to build. The most important thing, I think, that at this moment, most of goodness, most of services that all of us are using in a classic internet are based on not only on centralized solution, but also on the centralized data providers. I mean that almost 90% of the data itself is located on a classic database servers that are that has a real strictness about data modification, data loss, and other related stuffs. And if we want to try to replace them, if we want to try to build some kind of decentralized services, some kind of decentralized ecosystems, communities, we should try to find a solution how to solve this and how to provide a community really true, really mathematically proven concept that our data is consistent and wasn't modified by any kind of third-party service or any attacker. Let's think about what is data consistency in a nutshell. For example, if we have several parties that are communicating somehow, that are working on the same thing and are relying on a same data source, it's really important to each of them to be sure that no one of other parties are operating with invalid data or outdated data, that all of us are operating on actual data. Importance of these things rises up even more in financial world when we are really don't have a permission to operate on an outdated data or even to give some kind of third-party service or third-party attacker to try to modify the data itself. So how world is trying to solve this problem itself? The classic solutions, for example, are using some kind of several phases commits, but it's not about how to cover the data. It's not about how to prevent modification of the data. It's only about how to transfer some pieces of data to another machines and to be sure that each one machine in our cluster got it and accepted that piece of data. And the simplest solution that is available today is a one-phase commit. And all the things it's doing, it's simply has several related machines that are simply accepting pieces of data from one machine that has permission to push this data into the network. And this protocol is heavily used in classic replication solutions, in classic SQL databases, for example, Postgres or MySQL. It's a really base level of almost each one replication protocol. The next one is a two-phase commit. It's a little bit enhanced version of the one-phase commit. The thing it really makes it possible to each one machine in a cluster to be sure that all of them are operating on the same data. The logic is pretty simple. We have two phases. In first one, transaction manager or coordinator, as it could be called in some kind of specifications, collects the request from its client, and tries to prepare all the machines in the network. And in case if all one that is related to this transactions manager accepts these requests, then the transaction manager simply says, okay guys, we're ready to perform this operation. Let's try to push the data into the network. And after that, each one machine simply confirms that the data was accepted, write it on a stable storage, and in this case, transaction is expected to be done. The problems arise when the transaction manager is trying to be some kind of malicious actor or simply falls down. And in this case, we have a problem because each one related resource manager stays impossible to process the next transactions themselves. The next attempt that was performed by the community to solve the main problem of the Twophase commit is the Threephase commit. It's really really similar approach, and it provides one more state. And the main advantage of the Threephase commit is that in case if coordinator would go down, the participants would be able to process transactions they are involved at the moment, but they would not be able to process new transactions. Threephase commits only allows them to continue their work, and in case if coordinator does not begin available in the network itself, no one transaction can be performed after that. But in case if we are talking about some kind of decentralization, some kind of responsibility distribution, there is one more important problem. We should care not only about data replication itself, we should care about the trust to that data. We should care that in case if several parties are involved into the operation in a trustless environment, we should be able to know exactly that each one party that declares its agree to take part into the operation, that it would be performed in an expected way, and in case if it takes some kind of responsibility on it, that each one of us would be able to believe to each one of us exactly. So one of the approaches how to solve this complex task is HTLC. Please, guys and girls, raise up your hands in case if you don't know how the HTLCs exactly work. Okay, thank you. So it's a really true crypto community here. So most of us are knowing what is this, so I will try to cover it in a few words. It's a simple technique that all of us has to be sure that each one node that takes part into the operation does exactly that we are expecting it to do. So for example, if A would try to perform some kind of assets transfer to the E, we would be sure that A's assets would not be spent until it would be available to the E. But the main disadvantage of the HTLC itself is it not provides strict atomicity itself. Because in case if assets would arrive to the E would be able to use them, but D, C, B are under some kind of risk, because in case if some one of them would not fit into the timeout that is provided by the HTLCs itself, they are risking to lose their money. Interledger is trying to solve this maybe, but also to include several different ledgers into the operation itself, and to makes it possible to community to transfer assets between different ecosystems, for example, Bitcoin, Ethereum, maybe some kind of other ecosystems, and they are using almost the same solution in my vision. They only replaced one letter in its abbreviation. They are calling it not hash time locked contract. They are calling it hash time lock agreement, and they're trying to say, as guys, we cannot guarantee you that each one node in the operation would perform well, but we are expecting that each one node would perform well because they are risking with their money. So in case if they are some one of them would perform maliciously, in the worst case it will lose their money. But still, this solution is not atomic itself. Seller network, if you know what this project does, it uses pretty similar thing to the HTLA, but they are adding one more role into whole the system that is responsible for solving some kind of disputes that may arrive in classic HTLC. They call it PreImage Manager contract. And in case if Alice and Bob has some kind of dispute between them, they both are able to go to this some kind of dispute resolver and say, okay, smart contract, we have a problem here, can you please help us? And it simply tries to resolve this dispute and to provide them a final state between both of them. The main disadvantage of this solution is that, first of all, it's ecosystem locked, because at the moment they are unable to use this solution in environments that are different from the Ethereum itself. But in Ethereum itself, they are declaring that this solution works in pretty atomic manner. Okay, but if we are talking about real-world distribution, real-world decentralization, exchanging from transferring the responsibility from centralized solution to some kind of vendor-locked environment is pretty not enough in my vision. Notaries, one more item of the Interledger team. At the moment, as I know it, they are not continued developing this idea anymore, but it's really nice to know why they are dropped it. So the idea was simple. They are providing they wanted to provide a community with some kind of trusted source, some kind of this one guy, but in maybe some kind of decentralized solution, maybe, I don't know it. So the main role of the notaries should be pretty the same to the PreImage Manager contract in HTLR. So the Interledger team was expecting that each one member of the community would be able to go to the notary and say, we have a problem, can you please solve it? And all of the community must really accept the response from these notaries, and this is the main disadvantage. So in this case, each one of the notaries has a real potential to manipulate the balances of each one pair of the attendees in the network, and this is a really huge potential, and it's a really huge motivation to be malicious actor in my vision. So one more item to solve this really huge problem into the decentralized network. It's a technique called observers. Please imagine that we have 4 nodes that are involved into the operation, and we want to be sure that each one node has been processed the operation and has transferred its assets to its neighbor. What can we do in this case? So the atomicity itself is about 2 possible things. One of these things is decentralized consensus algorithms or ledgers. In these environments, members are forced to to somehow accept some of the variants of the network evolution itself. And the other thing, we may ask the participants of the network to perform in in an expected manner, and in case if they are not performing in an expected manner, only some kind of community members would be noted about it and would stop from communicating between between them. So, for example, if we are talking about some kind of decentralized ledger, for example, Bitcoin, there each one node, each one miner must be synchronized with each one another member. But if we are talking about networks like Lightning Network or Raiden or similar networks, in these networks, participants are trying to build their local consensus, and in case if one tries to cheat, only its neighbors, for example, this one and this one in this example, would stop from communicating with this malicious actor. So, for example, in case if node after the C is a malicious actor and the rest has been processed the operation, what should the network itself do? Please imagine that we have a decentralized environment where some kind of nodes are collecting compromises from the nodes that are unable to communicate with their neighbors and are unable to prepare some kind of local consensus. In this case, this node may go to the observer and say, okay guys, it seems that I took part into the transaction. It seems that I cannot have any response from my neighbors and even from other attendees of this operation. What should I do to simply continue this operation? Should I drop this operation, or in case it would be was finished, should I commit this? The next thing that observers does, they are simply go into each one participant of this operation and are asking, okay guys, I have some kind of complication from one of your friends, and he says that you are trying to perform some operation, and he says that he cannot contact you. Is it true that each one of you are trying to perform the operation itself? And in case if you're really trying to perform this operation, please send me some kind of a proof if you have this. So in case if the operation was really performed, each one node that was involved simply tries to push it, proof of that to the observer, and finally the node that cannot communicate with its neighbor simply goes to the external environment of observers chain, and gets it to itself. So in this case, the operation may be committed because each one node has its own proof that all of the nodes has been processed this operation itself. In case if observers are not able to communicate with nodes in this operation, or no one of them has an approved that operation was performed well, after some timeout, observers really write that, okay, we have a complaint from this node, but we have no any proofs that this operation was performed. So we simply say to these nodes that transaction itself should be rolled back. And I think that my deck would be incomplete if I would not mention about atomic swap, because it's really cool and really nice idea in a decentralized environments and decentralized community itself. The atomic swap is pretty cool technology. It enables us to swap exactly, not transfer assets between different ecosystems. The main disadvantage of this technique is that it supports only two parties. In case if we are trying to swap exchanges between more parties, we should perform several atomic swap operations and in some way try to achieve consensus between all of them. So thank you very much for your attention to this really complex deck. In case if you guys and girls have some questions to me, I would be really pleasure to answer.
Yeah, thanks, Dima. We have like time for a couple of questions. Yeah.
Thank you. So regarding that slide with observers, so what happens if only one observer, for example, can connect to other nodes, but other observers cannot connect? So what is the decision? Which observers
Okay, got it.
better?
Observers themselves are they are maintaining the common observers chain. One observer is only the participant of the network itself, but all of them are really forced to achieve some kind of consensus between all of them. And in case if one observer is reporting that, okay, I found this, approved that operation was performed, and other one says that I can't find it. Finally, after some time out, after some amount of blocks, they must achieve some kind of consensus on it. And in case, even in case if some one of them really found the approved that operation was performed, but was not written to the observer's chain, the operation must be rolled back on each one node.
Okay.
I want to ask you about atomic swap, but not your realization. About submarine swap.
We do not provide atomic swap.
Okay,
actually.
I mean, but you about submarine swap in Lightning Network. I know that you find some problem in submarine swap. Can you explain?
Actually, I'm not sure that this is a problem in atomic swap itself. Maybe it's a problem in one of implementation of the atomic swap. But maybe you have some specific question.
It's specific question about submarine swap realization in Lightning Network. Is it okay? Can we use it, or did you check it?
So okay, actually, I have not checked some kind of documentation of the Lightning community about the atomic submarine swap, but recently I met one team that is trying to implement it, and we have really discussed this approach, and there are really a problem in my vision. So I will try to explain you. So for example, we have 4 nodes, and as I know it. I may be not right. As I know it, Submarine Swap is trying to actually swap assets between the nodes, but in some kind of multi-hop manner. The main problem occurs in case if one of these hops is unable to perform the operation, and who the network must perform the operation backward. So the CE would get its assets back. But as our modeling shows us, it's almost really impossible in highly volatile networks, because assets configuration on these connections, on these channels, may be really different from that was on an operation start, and it may be unreal to revert some operation on these connections. So in case if atomic swap is really relying on operations rollback on each one of these hops, I think it's a really bad idea for them. So.
Okay, thanks, Dima. Thanks, guys, for a question again. Yeah, I
Thank
think
you very much.
Yeah, I think we'll have like 1 minute break now, because Andrei Sobol will be the next speaker. He's preparing now. Yeah, and all we need is just time to prepare. It's like 1-2 minutes. I ask you not to